Hi, hello, good morning, one and all. Welcome to the session. Can anybody confirm about audio and video? If audio and video both are good, then please do let me know about this one. Is everything okay? Hi, hello. Is audio and video both are clear? I hope this is clear. If anything goes wrong, please do let me know. Let me check from my side also. All right. Sure. So here, in the last session, we had a discussion on RL circuits. We had a discussion on RL circuits without sources. That means what? Source-free circuits where the inductor will be having some energy in it, and whenever you connect that inductor to the resistive network, the inductor will discharge its energy to the through the resistive networks. Okay. Now here RL circuits with sources. So the maybe the inductor may be charged inductor or maybe uncharged inductor. It doesn't matter. But if you are connecting these RL circuits with sources, now how will be the behavior or how will be the current variations or voltage variations across the inductor? You need to study. So it's all about we need to study about inductor, how the current is changing across the inductor, how the voltage is changing across the inductor. So the changes we need to observe IL of t, VL of t with respect to, that is inductor current with respect to time, and voltage across the inductor with respect to time. So that transitions you need to understand. The transitions we need to understand. Okay. So let us move. Let us move. Uh, just a minute. So let us move to the session. Move further. Okay. So before moving on to the session, there is a small introduction about myself. My name is Naveen. I have around 11 plus years of experience in teaching. Most of the times I'll be teaching electric circuits, machines, measurements and power systems. I did my masters in electric power systems from JT Hyderabad, and I cracked GATE and State Public Service Commission examinations too. I taught more than 20,000 students since 2012. So there's a small introduction about myself. Okay. So moving on further, here let me tell you the formulas or the formula behind the this RL circuit with the sources. Okay, so we need to observe the inductor current or inductor voltage. Here inductor opposes the sudden changes in current, right? Inductor opposes sudden changes in current. So let us have a look at that current equation. So the current equation will be generally IL of t is equals to IL of infinity plus IL of 0 minus IL of infinity into e power minus t by tau. Okay. So this is generally this is your equation. Okay. So infinity is nothing but steady state current, and this is initial current. This is initial current. We had a discussion how to calculate initial current, right? Initial current means before switching action. That's it. Before switching action. And again, this is again steady state term. So in source-free networks, in source-free networks, or circuits, if only inductor is having some energy in it and the inductor is connected to the resistive networks, and if you do not have a independent source, whatever the energy stored in the inductor will discharge through the resistive networks. So the final value is going to be definitely zero. In source free networks, the final value is going to be definitely zero. IL of the inductor current at t tends to infinity, after a long time, definitely the entire energy will be discharged. The entire energy will be delivered to the resistive network. So IL of infinity will be definitely 0 amperes. If IL of infinity is definitely 0 amperes, then what will be IL of t? IL of t is equals to, so this will be 0 and this will be 0. So you will be having only IL of 0 into e power minus t by tau. You will be having only IL of 0 into e power minus t by tau. Okay, is it visible? If not visible, let me write here. So then you'll get only IL of t is equals to IL of 0 into e power minus t by tau. This IL of 0 we write it as I naught. I naught into e power minus t by tau. Okay, all right. So this on this one we did some questions in the last session. Now let us discuss some questions. Let us discuss some questions with sources. Okay, okay. So with sources, let us see that, this is the equation. It will be useful to solve the questions, right? So let's move on. Right. What is asking? He is asking find I of t for t greater than 0. Find I of t for t greater than 0. Where is I? Where is I? Here is I. Here is I. Right. So we need to calculate the current flowing through the inductor. Current flowing through the inductor for t greater than 0. So here switching instant, you see the switching instant. Okay. So if you look at the switching instant, what he has given? He has given the switch is opened at t equals to 0. The switch is opened at t equals to 0. That means what? Switch is closed from minus infinity to 0 minus. T equals to minus infinity to 0 minus. Just before opening, 0 minus instant is nothing but just before opening the switch. Okay. So this is a long time, right? This is a long time, right? So if the switch is closed for a long time, now definitely this current source is going to is definitely connected with the network, and that current source will drive some current through the 10 ohm resistance, and it also drives the current through the inductor, and it will also drive the current through the inductor, and the current here after going through inductor, it will go through the short circuit because it's a switching element, it's a switching path only. Okay, so switching path is like a short circuit, 0 ohms path here. We do not have any element. So 0 ohms in parallel with 5 ohms. Obviously equivalent resistance is 0. So the entire current will divert through the switching path only. No current flows through this 5 ohm resistor. So I can write here at t is equals to 0 minus instant. That means what? Switch is closed from minus infinity to 0 minus. It's a long time, so I can say that it's steady state. In the steady state, inductor behaves like a short circuit. If inductor behaves like a short circuit, let me represent here. So here, this is my switching. This is the switching instant, and here is the inductor. Let me mention this as IL of 0 minus, and here I have got 10 ohms, and here I have got 6 amperes, like this. So this side anyhow you will be having 5 ohms, even though there is a 5 ohms, there is no use. Okay. Now this current source has to drive the current through the short circuit only here. No current flows through 10 ohms also, because you see 5 ohms, 10 ohms and this 0 ohms resistance are short circuit. All are connected in parallel. The equivalent resistance will be definitely 0. So this 6 amperes current source will drive the current through this inductor path and the switch path. So IL of 0 minus is equals to how much? You will get 6 amperes. No current flows through 10 ohms and no current flows through 5 ohms also, because of short circuit. Is it clear for everyone? Is it clear for everyone? Okay. So here, I got to know that the initial current through the inductor is 6 amperes, or IL of 0 minus, or you can also take up it as IL of 0 plus. Just after opening the switch also same current flows, that is 6 amperes, right? Now to solve this current equation, what I need? IL of t is equals to IL of infinity plus IL of 0 minus IL of infinity into e power minus t by tau. So in that I have calculated the initial value. The initial value is 6 amperes. Now I need to calculate the final value. Okay. So final value means, how do you calculate final value? So here at this point the switch is closed. Okay. Now at this point the switch is opened. So t equal to 0 minus instant is a long time, the switch is closed for a long time, and now the switch is opening at t equals to 0. Okay, after a long time t equals to infinity. So t equal to infinity means long time after opening the switch. Again this is a long time after opening the switch. After opening the switch. Again you can also call this as steady state. In the steady state inductor behaves like a short circuit. The steady state inductor behaves like a short circuit. Here also switch is closed. Switch is closed means the source might be connected, and because if the source is connected, the inductor will accept large current, and inductor will accept large current, of course constant current through it, and therefore there is no change in flux linkages and hence no EMF. So in the steady state here again it behaves like a short circuit. Now see, after opening the switch also, this will be IL of infinity, and here I have got 10 ohm resistor, here I have got 6 amperes current source. Now I am opening the switch here, and this side we have 5 ohm resistor. Okay, right. And now I want the current flowing through this path. IL of infinity is equals to, use current division rule. If you use current division rule, you will get it. 6 into opposite resistance divided by total resistance. 6 into 10 divided by 10 plus 5, 15. So 60 by 15. I think 15 fours of 60. So you will get it as 4 amperes. So this is the steady state current, or the final value current after opening the switch. Now if you write the equation, IL of t is equals to, IL of infinity is 4 and IL of 0 is 6 IL of infinity is 4 into e power minus t by tau. So I will get this equation as 4 plus 2 into e power minus t by tau. What is tau? What is tau? Tau is a time constant, right? A time constant within one time constant around 63.2% or 63.8% of total energy is going to be maybe dissipated or stored. Okay, here the source is connected. So inductor cannot dissipate now. Inductor is still under charging mode because the source is connected now. Okay, so this is the path. So inductor is charging, or inductor is storing the energy through which path? Through 5 ohms, and of course resistance through 10 ohms also current is flowing. Okay, so you need to take up the equivalent resistance from the inductor point of view. Then this will be 5 and here 10, and current source anyhow you have to open circuit it. So if you can calculate the R equivalent from here, don't calculate the R equivalent from the current source point of view. You should calculate the R equivalent from the inductor point of view, because inductor, at that point only you can find out charging or discharging path resistance or time constant. So the R equivalent is how much now? This 5 and 10 are looks like in series, so you will get R equivalent as 15 ohms. Now my tau will be L by R. How much is L? 1.5. So 1.5 divided by 15, you will get it as, I think 15 by 150, 1 by 10.1 seconds. So I can say 4 plus 2 into, so IL of t, how much I will get? 4 plus 2 into e power minus t by 0.1. So it will be minus 10 t amperes. Okay, what does it mean if you look at this one? If you look at this one, if you look at this network, the initial value of current is 6 amperes, right? Initial value of current through the inductor is 6 amperes. Final value of current through the inductor is 4 amperes. That means what? Inductor is decaying its energy after opening the switch. So if you draw the graph, it will be like this. If you draw the graph, it will be like this. Let me show you the graph also. So it looks like this. If I take up minus infinity, and this is IL of t, So the moment when you close the switch, it will not accept the current, and slowly it will accept the current exponentially, and it goes on to 6 amperes. Goes on to 6 amperes. So within 5 term constant, it will reach the 6 amperes, and then here let me take up t equal to 0. Now at this point I am opening the switch. If I open the switch, just after opening the switch, the same current will be maintained, no change in the current. T equal to 0 minus, T equal to 0 plus, the same amount of current will be there, 6 amperes current will be there. Now after some time constant, okay, after some time constant, so here for t greater than 0, what is the time constant? 0.1. So 5 time constants will be 0.1 into 5, so 0.5. So within 0.5 seconds, 5 time constants, it will reach to final value. How much? The final value is 4 amperes, maybe. So this might be 4 amperes, and this might be 6 amperes, and now then again this continues. T tends to infinity. This is how the graph looks like. Okay, initially the inductor is storing the energy because of 6 amperes current source, and the switch is closed, and then later the moment when the switch is opened, the inductor is not accepting the sudden changes in currents at t equal to 0. It is maintaining same 6 amperes t equal to 0 plus instant also. Now slowly, exponentially it is decaying its value. Within 5 time constant it will decay to 4 amperes, and it will reach to steady state again till you get disturbance. Okay, is this clear? Is this clear for everyone? Right. Look at this one. Find I of t for t greater than 0. Find I of t for t greater than 0. Here is the switching instant. So let us assume the switch is closed here. Here switch is opened at t equals to 0. That means switch is closed from minus infinity to 0 minus. Because I am opening the switch at t equal to 0, no? So it means the switch is closed from minus infinity to 0 minus. Now please be careful, don't just look at switching instant. You should also look at source, whether the source is connected or not also you should see. Now see, people will think that the switch is closed for a long time from minus infinity to 0 minus. Okay, so it's a long time. So because of long time, it's a steady state. And in the steady state, inductor behaves like a short circuit. So they will replace the inductor with short circuit, and they'll think that the 5 amperes current will flow through inductor, or as the switch is closed. Now, through which path they should flow? Through which path they should flow? Okay, here is a short circuit and here is a short circuit. Through which path they should flow? Right. So first of all, you see, if you close the switch at t equal to minus infinity, anyhow the inductor will oppose the sudden changes in currents, and definitely the entire 5 amperes current will flow through. There is no diversion, will flow through switch only, because the inductor will oppose the sudden changes in currents. It has some opposition. Resistance also has some opposition. So no current flows through inductor and resistance. The entire current flows through switch only. 5 amperes. That means inductor, the initial current, that means till 0 minus, the inductor not at all charged. Not at all, doesn't store any amount of energy. So IL of 0 minus is equals to 0 amperes simply. Even though source is connected to the network, but the source is driving the current through the short circuit path, that is switch path. Okay, so I can say that there is no energy stored in the inductor, and hence I can say that IL of 0 minus is 0 amperes. Now after opening the switch, I have 5 ohm resistor and I have an inductor, and the switch is opened here. So when you open the switch from t equals to 0 plus 2, t equals to infinity, this is a long time again. Now here, if I connect the current source of 5 amperes, now this 5 amperes current source can drive the current through 5 ohm resistor. Okay, and also it can drive the current through inductor. If the inductor is connected with respect to source, this source will drive the current, not immediately, not suddenly, but slowly or exponentially it will drive the current through the inductor. Yes or no? So that means what? It's a long time. This is a steady state. So steady state, in the steady state, inductor acts like a short circuit. Now this will become short circuit. So IL of infinity. How much you will get IL of infinity? 5 amperes. So the current equation will be IL of infinity will be IL of t is equals to IL of infinity is 5 plus IL of 0 is 0 minus IL of infinity is 5 into e power minus t by tau. So here 5 minus 5 into e power minus t by tau. This is my current equation. What is tau? Tau is the L by R. L value I know, that is he has given it as 2 henries. What is R value? So resistance of the path during charging or discharging. During charging or discharging, when the inductor is storing the energy or delivering the energy, through which path it is delivering or through which path it is storing the energy. Now as you see, the moment when you open the switch here, okay, so this current has to divert. Earlier the current was flowing through the switch. Now whenever you open the switch, there is no path now. Now it has to search for an alternate path. So immediately the current can be accepted by the resistance. Full amount of the moment when you open the switch, full amount of current, complete amount of current will flow through 5 ohm resistor, because inductor will not accept the sudden changes in currents. At t equals to 0 plus instant, inductor will behave like an open circuit. It will not accept the sudden changes in currents. When the switch is closed, 5 amperes is flowing and current through the inductor is 0. Now after opening the switch, the current through the inductor is still again 0, because it won't accept sudden changes in currents. So resistor has to accept the current, and slowly then some part of the current will divert through the inductor slowly. So 5 amperes initially at t equal to 0 plus, and then later some current will starts flowing through the inductor, and then current through the resistor will decrease. That's how. So what is while the current is accepted by the inductor, that's a charging process or storing the energy. The energy is stored in the inductor. So now what is the path now? This is a path. So this is my inductor, and with respect to this one I should connect. Now current source can be open circuited. Now R equivalent I am getting just 5 ohms. So 2 by 5, 5 4 is 20, so 0.4. I'll get, if I take a 0.4, 5 minus 5 into e power minus t by tau, 0.4 will be 10 by 4, it comes out as 2.5. 2.5 amperes. So if you draw the graph, how will be the graph? If you draw the graph, how will be the graph? The graph will be like this. Initially, from t equals to minus infinity to 0 minus, there is no current flow through the inductor. So simply I can take up 0. Now the moment when I open the switch at t equals to 0 plus instant, inductor will not accept the current, and slowly it will accept the current, and the maximum value is how much? The final value is how much? 5 amperes. Like this. And this will be achieved within 5 time constants. 5 time constant means 5 fours, 5 into 4, 5 into 0.4, you'll get it as within 2 seconds it will accept. Within 2 seconds it will reach 5 amperes. Okay, so this is how this graph, even you plot a graph also, this is how it looks like. You put t equals to 0, e power 0 will be 1, so 5 minus 5 will be 0, so you will get 0. And put 2 equal to 1 tau, put t equals to 1 tau. Okay, so if you go and solve that, you will get the answer. Put t equals to 2 tau, 3 tau, and so on, you will get the answer. This is how the inductor is going to change its current. So is it clear for everyone? And this kind of questions, switching, separate switching instance, very rare, but I expect for 2 marks. While solving these kind of questions, you must be very careful. Please understand the data what he has given. At t equals to 0, S1 is closed, and S2 is closed 4 seconds later. So if this is closed at t equals to 0, this is going to be closed at 4 seconds, t equal to 4 seconds or 4 seconds later. Now he's asking find I of t for t greater than 0. Calculate I for t equal to 3 seconds and t equals to 5 seconds. First of all, let us develop the equation for I of t. Let us develop the equation for I of t. Okay. Now, before closing the switch, you see from minus infinity to 0 minus. Okay, this switch is also open, this switch is also open. That means what? This source is not connected, this source is not connected. Only this resistor and inductor is available. And this, with respect to this resistor and inductor, no source is connected. If no source is connected, will it charge or will it store the energy? No, it will not store the energy and will not at all reach steady state. So at t equals to 0 minus, there is no current flowing through the inductor. So IL of 0 minus will be literally 0 amperes. No current because no source is connected. Okay. Now if I close the switch at t equals to 0 plus instant or t equals to 0, I am closing the switch. Switch 1 is closed. Okay. S1 is closed. Now if S1 is closed, now just after closing t equal to 0 plus instant, how the inductor will act? The inductor will act like an open circuit. The inductor will act like an open circuit because suddenly this source 40 volts voltage source is trying to drive the current through the inductor like this. But inductor will not accept. Inductor will take some time to rise the current. Yes or no? So t equal to 0 plus instant, now the current flowing through the inductor IL of 0 plus is again 0. Earlier how much current is maintaining at 0 minus, at 0 plus also same current maintains. Within 0 time it cannot accept the sudden changes in currents. Now as the time goes on, the change in current changes, flux changes, EMF induces and slowly EMF reduces, then current starts build up. Okay, so within 4 seconds it has to reach the steady state because I am closing the switch here. Let us see whether it is going to reach the steady state within 4 seconds or not. Okay, now let us assume final value IL of infinity is equals to. So if you allow this switch 1, the switch 1 for a long time, anyhow we are allowing the switch 1 for a long time. We are connecting the switch 1 at t equal to 0 and we are allowing it for a long time. So for a long time if you allow, the inductor will be acting like short circuit. If inductor acts like a short circuit, now this 40 volts voltage source can drive the current through the inductor like this. So how much is the current now? IL of t is equals to 40 divided by 4 plus 6. You will get it as 4 amperes. This is the final value of current. But we are not closing the switch 1. We are not just depending on switch 1 switching action. There is another switching action in between 0 to infinity. At 4 seconds instant itself, one more switching action is happening. So at 4th second again you will get a disturbance in the network. At 4th second again you will get a disturbance in the network because if this is also closed, now this source also will tries to drive the current now. Okay. So now let us see whether this 4 amperes final steady state value 4 amperes is reached before 4 seconds or not. Let us see. To see that you need to calculate the time constant. Now if you look at the time constant L by R, phi by R equivalent. Now can you tell me the R equivalent here? Can you tell me R equivalent here? So this inductor is storing the energy through which path? 4 ohms, 6 ohms and this path. There is the only path, na? So you can calculate from the inductor point of view 4, 6 and the voltage source must be short circuited. So R equivalent I will get 10 ohms. So 5 by 10 will be 0.5 seconds. So within 0.5 seconds around 63.2% of total energy will be stored, no? Or within 0.5 seconds 63.2% of 4 amperes will be gained by the inductor. Okay, let me show you the graph here. So if I close a switch at t equals to 0, 0 plus instant, there is no change in current. It is again still maintaining 0 current. Okay. Now within zero point 0.5 seconds, it has to reach 63.2% or 63.8% something. Okay. So 63%, let us take up 63% of total value. So 4 amperes, let me take up 4 amperes magnitude. So to reach 4 amperes, 5 time constant, you will get it as 5 into 0.5. You will get it as how much? 5 into 0.5? 2.5 seconds only. So within 2.5 seconds, it is going to reach the 4 amperes final value. Did you understand? That means what? Much before 4 seconds, much before closing the switch too. Okay, at 2.5 seconds itself, we are able to reach 4 amperes final value. No need to wait till infinity time constant. No need to wait till infinity instant. Okay, so much before closing the second switch, we are able to reach 4 amperes. Now the switching is taking place. At 4 seconds. Another switching. So at t equal to 4 seconds, the second switch is going to be closed. If the second switch is going to be closed, how will be the network now? If the second switch is going to be closed, how will be the network now? This is how it looks like. 4 ohms, switch 1 is closed, and here is a resistor. Here is a switch and resistor, voltage source. 6 ohms, inductor, 40, yeah, this will be around 40. It is 2 and 10. Right. Okay. Now, at t equals to 4 plus instant, just after closing the switch 2, then inductor behaves like an open circuit, right? So it will maintain the previous value of current. What is the previous value of current? 40 divided by 10, it will maintain 4 amperes. It will maintain 4 amperes. There is no change. Now, from t equals to 4 plus instant to t equals to infinity, if you allow it for a long time, then inductor will behave like a short circuit. So it is going to lose its previous value and it attains now the new value. So from 4 ampere state to the new value it will attain. So how to calculate this IL of infinity current now? You can use nodal analysis or mesh analysis. You can find out. Can you tell me by using nodal analysis? So to calculate IL of t, so V minus 40 divided by 4, V minus 10 divided by 2 and V by 6 is equal to 0. So if I take up V as common, 1 by 4 plus 1 by 2 plus 1 by 6. 1 by 4 plus 1 by 2 is, how much is that? 0.5, 0.75, 3 by 4. 3 by 4 plus 1 by 6. I'm getting around 11 by 2. Sorry, 11 by 12 is equals to, here constant 40 by 4 is 10. 10 by 2 is 5. So 10 minus 10 minus 5 will be minus 15. Standing on the right side, it will be plus 15. So V is equals to 15 12s. 15 by 11 by 12. 180 by 11. I am getting around 16.36. Okay. So if I get node voltage as 16.36, then what will be the current through inductor IL of infinity? 16.36 divided by 6. We will get it as 30 by 11 or otherwise 2.72 amperes. This is the final value of current, 2.72 amperes. Initial value of current, how much I have got? Around 4 amperes, na? 4 amperes. Now, from this 4 amperes, the graph we have drawn, na? From the 4 amperes, then the current has to decay to 2.72 amperes. So let me show you the graph. Let me show you the graph here. So the entire switching is taken place after 0 seconds only. We have already drawn this one. Let us assume this has 4 amperes and this is achieved within 2.5 seconds. Okay, right. Now we are closing the second switch at t equals to 4 seconds. Now at t equal to 4 plus seconds, how much you will get? 4 plus instant, same current has to be flow. Right. Now slowly it is going to happen. What is happening? The inductor current, initial current is decaying and the final value has to become 2.72. So if this is half to 2 and 2.72 will be near to 3. So probably somewhere here. So this is how it decays. Within how much time it has to decay? Within how much time it has to decay? If you calculate R equivalent, then it will looks like this. 2, 4, 6, and this voltage source should be short circuited. This voltage also should be short circuited, and you need to calculate R equivalent from these two. So 4 into 2, 8 divided by 6. 8 by 6 plus 6. So this is the equivalent resistance. I'm getting around 7.3 ohms. So what is tau now? L by R. L is of 2 henries, huh? Yeah, sorry, 5 henries. 5 by 7.3. I'm getting around 0.68. I'm getting around 0.68. This is the time constant. So 5 time constant means into 5. You will get it as 3.4 seconds. So from the 4th second to 3.4 seconds means 7.4 seconds. So by 7.4 seconds we will reach. So from here to here, this is a 5 time constant. So it will reach 2.72 amperes. Okay. So be careful. Here the equations are a little bit different. Here the equations are little bit different. Let me tell you the equations how we write. Okay. So here I have the initial value, I have the final value, right? So here I can write the inductor current equation till second switch closes, till the second switch closes. So I can write IL of t is equals to, IL of infinity is how much? Not infinity actually, the 4 amperes only, till 4 seconds only, till 4 minus seconds only. How much it is? I can write it as 4 amperes. So 4 plus initial value is 0, 0 minus 4 into e power minus t by tau. So I can write 4 minus 4 into e power minus t by tau. What is the tau value? Tau value we have got it as around 0.5. That is around 0.5 means you can write it as 1 by 2 or 2t. So this is the equation. But when it comes to second instant, how you should write here? IL of t, you should not write t. This is t, the switching is happening after 4 seconds or at 4 seconds. So t minus 4 you need to take up. T minus 4 you need to take up. Okay, so here I can write the IL of t minus 4 instant will be taken as, what is the final value? The final value is 2.72 plus, what is the initial value? Initial value is 4. What is the final value? 2.72 into e power minus t minus 4 by tau. Okay. So you'll get 2.72 plus 4 minus 2.72 is something you'll get 1.28 into e power minus t minus 4 by tau. Anyhow, tau we have got this 0.67681. Like that you can substitute. So this is the current equation. So be careful. The switching instance if separated, then be careful. Okay. Even you did wrong also, even you take up with IL of t is equal to 2.72 into e power, that is 4 minus 2.70 into e power minus t by tau. Whenever you are substituting t value, you will get to know. If you substitute t is equals to 5 seconds, how much current you should get. If you substitute t is equal to 3 seconds, how much current you should get. Okay, let me show you. In the question he asked, see, he has asked current t at t equal to 3 seconds, at t equals to 5 seconds. That means at t equal to 3 seconds. 3 means here I'm switching at 4 seconds. Nah? So 3 seconds may be here, 3 seconds may be here. At 2.5 seconds itself the current is 4 amperes. Now at 3 seconds definitely it is 4 amperes. Nah? Definitely it is 4 amperes. Nah? Now at t equals to 5 seconds. At 4 seconds the current is 2.72. Now at 5 seconds, at t equals to 5 seconds, definitely it is less than 2.72. I of 5 seconds will be less than 2.72 and greater than 2.72. So to find out this current you need to substitute 5 here. So 5 minus 4 and the like that you can substitute. If you can substitute you will get the answer. Okay. Is it clear for everyone? So this is how we take up the RL networks with sources. So whether it is with sources or without sources, this equation you need to remember: final value, initial value minus final value into e power minus t by tau. So for source free network, simply the final value will be 0. IL of infinity will be 0. Therefore, the current equation will be, inductor current equation will be IL of 0 minus IL of 0 into e power minus t by tau. So this is, we write it as I naught into e power minus t by tau. With sources, you can take up this. Without sources, you can take up this. You can, without source, obviously the final values will be 0. You can use this equation itself. No issues. Anyhow, final values will be 0. If you substitute 0, again the equation will turn out to be like this. Okay. All right. So this is, about something RL circuits, right, with sources. Tomorrow we'll see RC circuits. Okay. Have a nice day. Bye bye. See you. If you have any doubts, you can reach out to me on my mail ID or my mobile number.